Welcome. Now let's look at the fundamental theorems of limitation. But before that, what is the meaning of limit of a function? The limit of a function is the value that function approaches when the input tends to a set of values. For instance, if limit 2x plus 5 when x tends to 4. So what will be the value of this limit of the function? Now let's look at it together. The limit 2x plus 5 when x tends to 4. This means that 4 is our target and there will be a set of values starting from 4. So we have 4. When x is increasing, we can have 4.001, 4.01, 4.1, and so on like that. So when x is decreasing, we can have 3.999, 3.99, 3.9, and downward like that, and so on. So this means when x is less than 4, and the other side is when x is greater than 4. Now let's consider the set of value. This is our set of value from 3.9, 3.99, 3.9994, and so on like this, and this also. Now recall that 2x plus 5 is our function. So when x is equal to 3.9, starting from the lowest in our set of value. So 2 into brackets 3.9 instead of x plus 5 is equal to 2 times 3.9, that is 7.8, plus 5 is equal to 12.8. And when x is equal to 3.99, we have 2 into brackets 3.99 plus 5. This is equal to 7.98 plus 5, which is 12.98. The one that is closer to 4, which is x is equal to 3.999. So we have 2 into 3.999 plus 5, and this will be equal to 12.998. Now let's move on. So when x is equal to 4, we have 2 into 4 plus 5, which is equal to 8 plus 5 is equal to 13. Now when x is greater than 4, we have x is equal to 4.001. So 2 into 4.001 plus 5 will be equal to 13.002. And when x is equal to 4.01, therefore 2 into 4.01 plus 5 will be equal to 13.02. Then when x is equal to 4.1, we have 2 into 4.1 plus 5, which is equal to 13.2. Now let's check it together. We have when x is less than 4, our set of value for the limits are 12.8, 12.98, 12.998, and when x is equal to 4, our value is 13. And the last one, when x is greater than 4, our set of values are 13.002, 13.02, and 13.2. Actually, it's more than this, but we will just consider the set of value we evaluated. Now, having looked at it, we can see that x is equal to 4 is our target, which its value is 13. And when x is less than 4, we can see that it approaches to 12.998. And when it's greater than 4, it approaches to 13.002. Now you can see that both 12.998 and 13.002 are both very close to 13. So the limit of 2x plus 5 when x tends to 4 is 13. Hope this is clear. Thank you. So if limit of function f of x when x tends to a is equal to p, this means that the p is the limit of the function f of x as x approaches or tends to a. Note that limit enhances problem solving in differentiation and integration. Now let's look at the fundamental theorems of limits. The first theorem: the limit of a constant is the constant, that is, limit of c when x approaches to a, it is equal to c, where c is a constant. Then the second theorem is the limit of a sum or difference, which is addition or subtraction, is the sum or difference of an individual limit. That is, limit of f of x plus or minus g of x when x approaches to a is equal to limit of f of x when x approaches to a plus or minus limit of g of x when x approaches to a. The third one is the limit of a product, which is the product of individual limits. That is, limit of f of x times g of x when x approaches to a is equal to limit of f of x when x approaches to a times limit of g of x when x approaches to a. Now, theorem 4, which is the limit of a quotient. That is, limit of f of x over g of x when x approaches to a is equal to limit of f of x when x approaches to a over limit of g of x when x approaches to a. This means that the limit of a quotient will form a quotient limit of individual functions. Now, the last theorem is the theorem of a radical. That is, if you have limit of nth root of f of x when x approaches to a will be equal to nth root of limit f of x when x approaches to a. Now, let's look at some techniques of evaluating limits. These are the techniques of evaluating limits, and we are going to take them one after the other to evaluate different limit problems. Now, let's start with direct substitution. Now, let's look at some examples. So, Example A, we have limit of 9 when x tends to 2. Recall that in the first fundamental theorem, which is the limit of a constant, so d is equal to 9. Example B, we have limit of 3x raised to power 2 when x tends to 0. So this is equal to 3 into 0 all raised to power 2. It is equal to 0. Then example C, we have limit of x raised to power 2 minus 5x plus 6 when x tends to 1. So this is equal to 1 raised to power 2 minus 5 into 1 plus 6, which is equal to 1 minus 5 plus 6, and the value is 2. So example D, we have limit x plus 2 in bracket and x minus 3 in bracket when x tends to 0, which is equal to 0 plus 2 in bracket, another bracket 0 minus 3. So this is equal to 2 multiplied by minus 3, which is minus 6. Now example E, we have limit of 2 plus 3x over 5x plus 1 when x tends to 2, which is equal to 2 plus 3 into 2 over 5 into 2 plus 1. This is equal to 2 plus 6 over 10 plus 1, which is equal to 8 over 11. Now let's look at another example. Example F, we have limit of square root of x raised to power 4 minus x plus 7 when x tends to minus 1. This is equal to square root of into minus 1 raised to power 4 minus into minus 1 plus 7. So this is equal to square root of 1 plus 1 plus 7 is equal to square root of 9, which is equal to 3. Thank you. Now let's move on to the next techniques. But before we continue, in the direct substitution, you will have noticed that we substitute directly of the value which x approach to, but some of the limits cannot be substituted directly because they can either lead to an undefined or indeterminate form. Therefore, factorization methods can be used to solve some of them. Now let's look at some example. Example A, we have limit of 5x raised to power 2 minus 3x over 9x when x tends to 0. If we look at this closely, we notice that the denominator cannot be substituted directly with 0 because the denominator will be equal to 0, which is an undefined, and there won't be any value for the limits. So this can be solved by factorizing x out of the numerator. Therefore, this will be equal to limits when x tends to 0 of x into 5x minus 3 over 9x. So x, we cancel x. So this will remain limit when x tends to 0 of 5x minus 3 over 9, which is equal to, by substituting 0 now, we have 5 into 0 minus 3 over 9 is equal to 0 minus 3 over 9. So it's left minus 3 over 9. 3 goes in 3, we have 1. 3 goes in 9, we have 3. So it's left minus 1 over 3. So another example B, we have the limit of x minus 4 over x raised to power 2 minus 16 when x tends to 4. This cannot be solved directly as well. So we have limits when x tends to 4, x minus 4 over, look at the denominator. This is an example of difference of 2 square. So x raised to power 2 minus 16 is also equal to x raised to power 2 minus 4 raised to power 2. So which is x minus 4 into x plus 4. Now we have x minus 4 into x plus 4. So x minus 4 will cancel each other. So it left limits when x tends to 4 into 1 over x plus 4. Now let's substitute. We have 1 over 4 plus 4 is equal to 1 over 8. This is the answer for these limits. Now let's look at another example. So example C, we have limits of x plus 2 over x raised to power 2 minus x minus 6 when x tends to minus 2. So this is equal to limits when x tends to minus 2 into x plus 2. The denominator is a quadratic expression. So this is the first method to solve it. X here, the other x here. So the product is minus 6. And the sum will be, the product must be a factor of 6. And it must equals to minus 1. So minus 3 plus 2. So here we have plus 2 and here minus 3. So x plus 2, we cancel x plus 2. And this will equal to limits when x tends to minus 2 into 1 over x minus 3. Now let's substitute. We have 1 over minus 2 minus 3 is equal to minus 1 over 5. Now another example D, we have limits of x raised to power 2 plus 4x minus 21 over x plus 7 when x tends to minus 7. Now the numerator is a quadratic expression. So we have limit when x tends to minus 7 into, now like we saw the other one, open 2 brackets. Now the product is 21, and each factor is 7 and 3, and the sum must be equal to plus 4. So we have plus 7 and minus 3. So x here and the other x here, plus 7 minus 3 over x plus 7. So x plus 7 we cancel each other. So it's left x minus 3. Now we have limits when x tends to minus 7 into x minus 3. Now it's time to substitute for minus 7. So we have minus 7 minus 3, which is minus 10. Now another example, we have limits of x raised to power 2 minus 3x minus 40 all over x squared minus 8x when x tends to 8. Now this is equal to limits when x tends to 8 into bracket, product is 40 for the numerator, and the sum will be, the factors of 40 is 8 and 5, which can equal to 3. And to get minus 3, we have minus 8 plus 5. Now let's substitute. So open two brackets. So x here and the other x in the other side. Minus 8 plus 5 over, this also we can factorize x out of the denominator. So we have x into x minus 8. So x minus 8 will cancel each other, and this will left limits when x tends to 8 into x plus 5 over x. Now let's substitute. 8 plus 5 over 8 is equal to 13 over 8, and this is the same thing as 1 whole number 5 over 8. Thank you. Now let's move on. Another example F. The limit of x raised to power 3 minus 1 over x minus 1 when x tends to 1. Now for this one, you can see that x raised to power 3 minus 1 is also the same thing as x raised to power 3 minus 1 raised to power 3, and this can be factorized by using this formula. A raised to power 3 minus b raised to power 3 is equal to a minus b into a raised to power 2 plus ab plus b raised to power 2. Therefore, x raised to power 3 minus 1 raised to power 3 is also equal to x minus 1 into x raised to power 2 plus x times 1 is x, so plus x plus 1 raised to power 2, which is 1. Now let's substitute for this. So we have the limit when x tends to 1. This will become x minus 1 into x raised to power 2 plus x plus 1 over x minus 1. So x minus 1 will cancel each other. So it's left limits when x tends to 1 into x raised to power 2 plus x plus 1. So this is 1 raised to power 2 plus 1 plus 1, which is equal to 3. Now, one more example. Example G. You have limits of x raised to power 3 plus 3 raised to power 2 plus 2x all over x raised to power 2 minus x minus 6 when x tends to minus 2. In this expression, there is two things there. We have quadratic expression and we can also factorize x out. So this is equal to limit when x tends to minus 2. Factorize x out of the numerator. We have x into x raised to power 2 plus 3x plus 2 all over x raised to power 2 minus x minus 6. So we have quadratic expression now. Solving the quadratic expression, we have limits when x tends to minus 2 into bracket x. For the quadratic expressions, open two brackets for the numerator and for the denominator. Now, so 2 is the product for the numerator and the sum must be plus 3. So we have plus 1 and plus 2. For the denominator, 6 is the product and the sum must be minus 1. Since our product is 6 and each factors 3 and 2. So to get minus 1, this is minus 3 and plus 2. We can now see that x plus 2 will cancel x plus 2. So it will left the limit when x tends to minus 2 into x plus 1 over x minus 3. We can substitute now for minus 2. So minus 2 into minus 2 plus 1 over minus 2 minus 3. So this is equal to minus 2 and the bracket will equal to minus 1 over minus 5. So this is equal to minus 2 over 5. The numerator minus 2 times minus 1 will be equal to 2 and the numerator have minus. That is why it's equal to minus 2 over 5. Thank you. We will continue in the next video. Don't forget to subscribe. Meet you in the next video. Thanks for watching.